on the sun-scorched coast of South Texas, where the Gulf of Mexico meets one of America's busiest shipping channels. Engineers are attempting something that has never been done before on this continent. Two colossal towers rise 538 feet into the Texas sky, taller than the Statue of Liberty, from base to torch. Between them stretches a single, breathtaking span of 1,661 feet, suspended by cables, so precisely engineered that each strand could support the weight of 50. This is the new Harbor Bridge, and when complete, it will claim the title of the longest cable-stayed concrete bridge in North America. The existing Harbor Bridge has served Corpus Christi since 1959. But after 6 decades of relentless Gulf Coast weather, millions of vehicle crossings, and the explosive growth of the Texas energy industry, this aging structure can no longer meet the demands of modern commerce. Ships have grown too large, traffic has grown too heavy, and the economic stakes have grown too high. The solution? A $1.1 billion megaproject that will redefine what's possible in American bridge construction. But building a record-breaking bridge over an active shipping channel, one that handles 500 vessels per month carrying petroleum, chemicals, and liquefied natural gas, presents challenges that would make most engineers reconsider their career choices. Hurricane-force winds, extreme heat, salt-laden air that devours steel like acid, and tolerances so tight that a deviation of just 2 centimeters could compromise the entire structure. This is the story of how a team of thousands is conquering those Challenger 1 cable, one concrete segment, one impossible day at a time. Welcome to the construction of the Harbor Bridge. Before a single foundation could be poured, engineers faced a logistical puzzle of staggering complexity. This wasn't just building a bridge, it was orchestrating a construction ballet on one of America's most strategically important waterways. The Corpus Christi Ship Channel is no ordinary body of water. It's the economic artery of the Texas Gulf Coast, handling over 100 million tons of cargo annually. Petroleum refineries, chemical plants, and liquefied natural gas terminals line its shores. Every hour of channel disruption costs the regional economy millions of dollars. The project team's first challenge was deceptively simple. How do you build a massive bridge without stopping the ships that pass beneath it? The answer required years of planning before the first shovel touched dirt. Engineers developed a phased construction strategy that would maintain shipping traffic throughout the entire build. The new bridge would be constructed alongside the existing structure, allowing the old bridge to continue carrying 23,000 vehicles daily while its replacement took shape. Site preparation began with something that sounds mundane but proved extraordinarily complex: utility relocation. Beneath the streets of Corpus Christi and the waters of the ship channel lay a tangled web of infrastructure: water mains, sewer lines, natural gas pipelines, fiber optic cables, and high-voltage electrical conduits. Moving these utilities required 18 months of careful excavation and rerouting, at a cost exceeding $50 million. Building information modeling, or BIM, became the project's digital backbone. Engineers created a complete 3-dimensional virtual replica of the bridge, the ship channel, and every piece of underground infrastructure. This digital twin allowed teams to simulate construction sequences, identify potential conflicts, and coordinate the work of dozens of contractors before breaking ground. Access proved equally challenging. The bridge spans not just water but a complex patchwork of industrial facilities, rail lines, and residential neighborhoods. Engineers constructed dedicated haul roads capable of supporting the project's heaviest equipment: concrete trucks, crawler cranes, and specialized transporters carrying bridge segments, weighing hundreds of tons. Soil conditions along the Texas coast presented their own complications. The ground here is a mixture of clay, sand, and ancient marine sediments, stable enough for houses, but far too weak to support a structure of this magnitude. Extensive geotechnical surveys mapped the subsurface conditions at hundreds of locations, guiding engineers to design foundations that would reach far beneath this unstable layer to the solid strata below. The preparation phase also required something unprecedented in Texas bridge construction: a hurricane response plan. The Gulf Coast averages one significant hurricane strike every 3 years. Engineers developed detailed protocols for securing construction equipment, protecting partially completed structures, and resuming work after storms. These plans would be tested sooner than anyone hoped. The new harbor bridge would be only as strong as what lies beneath it, and for a structure designed to carry 90,000 vehicles per day while resisting hurricane winds, exceeding 150 miles per hour. Strong enough takes on an entirely new meaning. The foundation challenge began with geology. The Texas coastal plain consists of layer upon layer of sediment deposited over millions of years, soft clays, loose sands, and compressible silts that would settle under the bridge's immense weight. Engineers needed to reach more competent material, sometimes 100 feet below the surface. For the approach structures, construction crews drove hundreds of concrete piles deep into the earth. These weren't ordinary piles. They were 24-inch square concrete columns, reinforced with steel rebar and driven by diesel hammers delivering 100,000 foot-pounds of energy with every blow. The rhythmic thunder of pile driving became the heartbeat of the project, audible 4 miles across the coastal plain. But the main towers demanded something far more substantial. Each tower would support approximately 50,000 tons of bridge deck and cable tension, forces that would crush conventional foundations like empty soda cans. Engineers designed massive drilled shaft foundations, each one 10 feet in diameter and extending 120 feet below the surface. Creating these shafts required specialized drilling rigs equipped with augers the size of small cars. The rigs bored through layer after layer of soil, extracting thousands of cubic yards of material from each shaft location. Workers then lowered cylindrical rebar cages, intricate structures containing 60 tons of reinforcing steel into the excavations. The concrete pour for each foundation shaft was an engineering event unto itself. High-performance concrete, specially formulated to resist the corrosive effects of Gulf Coast salt water, was pumped continuously for up to 18 hours. The mix included supplementary side materials fly ash and silica fume that would react chemically over time, creating a matrix nearly impervious to chloride penetration. Temperature control proved critical during curing. Concrete generates tremendous heat as it hardens, a chemical reaction called hydration. In the massive foundation shafts, internal temperatures could exceed 160 degrees Fahrenheit, creating thermal stresses capable of cracking the concrete from within. Engineers embedded networks of cooling pipes through the rebar cages, circulating chilled water to control the temperature differential. The tower foundations required additional innovation. Each main tower sits on a pile cap measuring 80 feet by 50 feet, a concrete platform connecting multiple drilled shafts into a single, unified foundation. These pile caps contain over 3,000 cubic yards of concrete and 500 tons of reinforcing steel, formed and poured in carefully sequenced lifts to prevent thermal cracking. Workers then constructed concrete pedestals atop the pile caps, massive blocks that would support the tower legs. Every surface was checked with laser surveying equipment, ensuring that the towers would rise with perfect verticality. At these stays, tolerances were measured in fractions of an inch. Any deviation would compound as the towers rose, potentially throwing the entire bridge geometry out of alignment. With foundations complete, the Harbor Bridge project entered its most visually spectacular phase. The rise of the main towers and the cable-stayed spans that would make this structure unique in North American engineering. The towers themselves are architectural and structural statements, rising 538 feet above the waterline. They're designed in a distinctive inverted washaptu, inclined legs meeting at a single peak. This geometry isn't merely aesthetic, it's optimized to resist the complex forces that cable-stayed bridges experience, channeling tension from the cables down through the angled legs and into the foundations below. Constructing these concrete giants required a specialized technique called slip forming. Workers assembled a climbing formwork, systems massive steel molds that could be raised incrementally as each section of concrete cured. The process operated continuously, 24 hours a day, 7 days a week. Fresh concrete was pumped into the forms from below while the cured sections emerged from the top, rising at a rate of approximately 10 inches per hour. The precision required was extraordinary. Survey teams monitored the tower geometry constantly, checking for any deviation from the design alignment. Adjustments were made in real time, tweaking the formwork position by fractions of an inch to keep the towers climbing perfectly vertical. A 2-inch error at the base would translate to a 2-foot error at the top end. Unacceptable deviation for a cable-stayed structure. The concrete mix for the towers was specially engineered for the Gulf Coast environment. Standard Portland cement concrete would deteriorate within decades under the assault of salt spray, humidity, and temperature cycling. Engineers specified a high-performance mix with a design life exceeding 100 years, incorporating corrosion-resistant reinforcing steel and supplementary cementitious materials. As the towers rose, workers began preparing for the bridge deck itself. Unlike suspension bridges, where the deck hangs from cables draped between towers, cable-stayed bridges support their decks directly from cables anchored to the tower. This design allows for longer spans with less material, but requires extraordinary precision in cable installation. The deck construction employed the balanced cantilever method, technique that sounds simple but demands extraordinary coordination. Starting from each tower, crews built the deck outward in both directions simultaneously, maintaining perfect balance to prevent overturning forces. Each new segment was cast in place, extending the cantilever by approximately 16 feet at a time. Massive form travelers' movable platforms weighing 500 tons supported the construction of each deck segment. These mechanical marvels cantilevered beyond the completed deck, providing a platform where workers assembled rebar, installed tendons, and placed concrete. Once a segment cured and achieved sufficient strength, the form traveler advanced to the next position, and the cycle repeated. The stay cables themselves represent state-of-the-art technology. Each cable consists of multiple 7-wire strands, protected by high-density polyethylene sheathing and anchored in massive steel housings at both the tower and deck. The cables are installed one strand at a time, then stressed to precisely calculated tensions using hydraulic jacks, capable of generating 1,000 tons of force. As each pair of cables was installed, the deck segment they supported transferred its weight from the form traveler to the cable system. This allowed the form travelers to advance, continuing the cantilever extension. The process repeated dozens of times on each side of each tower, gradually extending the deck toward the center of the main span. The moment of closure when the two cantilevers finally met at midspan represented the engineering climax of the project. The final segment, cast with millimeter precision, had to fit perfectly between the approaching deck ends, while maintaining the design geometry of the entire structure. Survey teams worked 4 weeks beforehand, measuring and remeasuring to ensure that the closure would proceed without incident. Building the longest cable-stayed concrete bridge in North America was never going to be easy, but the Harbor Bridge project faced challenges that tested even veteran engineers. The Texas Gulf Coast experiences some of the most demanding construction conditions in America. Summer temperatures regularly exceed 100 degrees Fahrenheit, with humidity levels that make the air feel like a sauna. Workers faced heat indexes approaching 115 degrees, requiring mandatory cooling breaks, hydration stations, and modified work schedules that shifted heavy labor to early morning and evening hours. Concrete placement became a temperature-sensitive operation. At high temperatures, concrete sets faster, sometimes too fast, creating quality problems. Engineers adjusted mix designs continuously, adding ice to the concrete trucks, and scheduling pours during cooler periods, curing blankets, misting systems, and reflective covers protected fresh concrete from the brutal sun. But summer heat was almost welcome compared to what the Gulf of Mexico could deliver. Hurricane season runs from June through November, and the project faced several close encounters with tropical systems. Hurricane Harvey in 2017 brought devastating flooding to the Houston area and disrupted supply chains throughout Texas. Subsequent storms required evacuation of construction personnel and securing of equipment and materials. The project developed sophisticated weather monitoring protocols. Meteorologists tracked tropical systems days in advance, providing early warning for preparation activities. Cranes were lowered and secured. Loose materials were tied down or removed. Foam travelers were locked in position. The goal was to resume construction within hours of storm passage, minimizing schedule impacts. Wind presented challenges, even without hurricanes. The design wind speed for the completed bridge is 150 miles per hour, sufficient to withstand the most intense hurricanes. But during construction, the partially completed structure was more vulnerable. Engineers calculated wind limits for every construction activity, suspending work when gusts exceeded safe thresholds. The marine environment attacked materials with relentless chemistry. Salt spray carried by Gulf breezes deposits chlorides on every exposed surface, Given enough time, these salts penetrate concrete and corrode the reinforcing steel within, a process that has shortened the lifespan of countless coastal structures. The harbor bridge team specified materials and coatings designed to resist this assault for a century or more. Quality control reached levels approaching aerospace manufacturing. Every batch of concrete was tested for strength, workability, and air content. Every rebar cage was inspected before concrete placement. Every cable strand was proof tested before installation. The project maintained laboratories on site, with technicians running tests 24 hours a day. Survey accuracy was equally critical. The geometry of a cable-stayed bridge is precisely calculated cable tensions. Deck, elevations, and tower positions are all interdependent. An error in one location affects the entire structure. Survey crews used satellite positioning systems, accurate to within millimeters, cross-checked by optical instruments, measuring angles and distances with extraordinary precision. Digital technology transformed construction management. Real-time monitoring systems tracked concrete temperatures, cable tensions, and structural movements. Building information modeling coordinated the work of hundreds of engineers, contractors, and suppliers. Drones provided aerial photography for progress, documentation, and inspection access. The harbor bridge became a showcase for 21st century construction technology. When the final cable is tensioned and the last barrier removed, the new harbor bridge will transform the Corpus Christi region in ways that extend far beyond transportation. The economic impact begins with the bridge's primary purpose, enabling larger ships to reach the port of Corpus Christi. The existing bridge provides only 138 feet of vertical clearance, insufficient for the largest modern cargo vessels. The new bridge raises that clearance to 205 feet, accommodating the fully loaded supertankers and container ships that dominate 21st century maritime commerce. This increased clearance arrives at a critical moment. The port of Corpus Christi has become America's largest exporter of crude oil, shipping millions of barrels daily to refineries around the world. The shale revolution transformed Texas into an energy superpower, and Corpus Christi became its primary gateway to global markets. Without the new bridge, this growth would hit a literal ceiling. The transportation benefits extend to the 90,000 vehicles expected to cross daily. The new bridge provides 6 lanes compared to the existing structure's 4, with modern safety features, including wider shoulders and improved sightlines. Commuters will save time. Emergency responders will reach incidents faster. Commercial traffic will flow more efficiently between the port facilities and the regional highway network. The old harbor bridge, after serving Corpus Christi faithfully since 1959, will be carefully demolished. This process itself represents an engineering challenge, requiring removal of 84,000 tons of steel and concrete from above an active shipping channel. The demolition will provide jobs, generate recyclable materials, and remove a structure that had become a bottleneck for regional growth. Environmental considerations shaped the project from inception. The new bridge's longer span means fewer piers in the water, reducing impacts on the ship channel ecosystem. Stormwater management systems capture and treat runoff before it reaches the bay. The improved traffic flow will reduce vehicle emissions, as cars and trucks spend less time idling in congestion. The harbor bridge also represents a statement about American infrastructure capability. For too long, the United States has fallen behind other nations in building major public works. The harbor bridge proves that American engineers, American workers, and American materials can still create world-class infrastructure structures that will serve communities for generations. For the people of Corpus Christi, the bridge means something more personal. It's a symbol of their city's growth, their port's importance, and their region's future. Children born today will cross this bridge throughout their lives, taking for granted the engineering marvel that their parents watched rise from the coastal plain. 750 feet above the ship channel, at the peak of the main towers, workers installed the final sections of concrete that will anchor the cable system. They paused for photographs, knowing they stood atop something historic, the tallest bridge towers in Texas, supporting the longest cable-stayed concrete span in North America. From that vantage point, they could see tankers waiting to load crude oil. They could see refineries processing fuel for the nation. They could see the city of Corpus Christi spreading across the coastal plain and connecting it all. They could see their bridge, the new harbor bridge, rising from the Texas coast like a monument to human determination. A bridge that skeptics said would face too many challenges, A bridge that engineers said pushed the boundaries of concrete construction. A bridge that workers built through hurricanes and heat waves and a global pandemic. The harbor bridge, built to last a century. Built to transform a region. Built to prove that in America, we can still build great things.